Hello and welcome to my lecture on list homomorphism problems for sine graphs. I am Jan Bok and this is a joint work with Richard Brewster, Thomas Feder, Pavel Hell and Nikolai Lichkova. First of all, let me recall a basic notion of graph homomorphism. We say that F is a graph homomorphism if it is a mapping between the vertices of G and the vertices of H, such that whenever we have an edge between U and V in G, there is also an edge between FU and FV in H. That means that graph homomorphisms are adjacency-preserving mappings between the vertex sets of two graphs. In the figure below, the bipartite cycle of size 8 is homomorphic to the graph composed of one edge. That is because we can map the vertices of one part to the one endpoint and the second part to the other endpoint. In this talk, we are interested in sine graphs. These were first studied by Koenig and Harari, and an intensive research has later begun with several papers of Zaslavsky. A sine graph is a pair composed of a graph G and a signing function sigma, assigning to every edge of G either plus or minus. We call G the underlying graph. For the sake of simplicity, different edges between the same two vertices have different signs. Because of that, there are at most two edges between the same vertices. I denote negative edges by red color and positive edges by blue color. This can be seen in the figure below. An important operation is the switching operation. This can be applied to any vertex of a sine graph, and it results in multiplying signs of all its incident edges by -1. We further say that two graphs are switching equivalent if we can obtain one from the other by a sequence of switchings. For example, in the figure below, we can get the graph on the right from the graph on the left by switching at the highlighted vertices. We can also define the sign of a cycle, which is the product of the signs of its edges. We distinguish between a negative cycle and a positive cycle. The graph on the left has 3 negative edges, therefore it is negative. The one on the right is composed solely of negative edges. However, it has even number of negative edges, and so it is a positive cycle. Even more important notion is the notion of balancedness. We say that the sine graph is balanced if every cycle in the graph is positive, and anti-balanced if every cycle in the graph is negative. It is known that the sine graph is balanced if and only if it is switching equivalent to a sine graph with all edges positive, analogously for anti-balanced graphs. This is one of the basic results proved by Zaslavsky. The graph on the right has a negative cycle. However, it has two blue loops which will be preserved no matter how we switch. Therefore, it is a non-balanced graph. The graph on the left is balanced since we can switch in the highlighted vertices to obtain a graph with just blue edges. Now I can finally proceed to the main definition of the talk, homomorphism of sine graphs. Homomorphism of sine graphs is a mapping between the vertex sets of two sine graphs, such that there exists a graph switching equivalent to the source graph, so that not only adjacencies are preserved, but also the colors of edges. A positive edge goes to a positive edge, and the same holds for negative edges. We note that without the possibility of switching, we would get homomorphisms of two edge-colored graphs. We can also associate a computational problem to this definition. Let HP be a fixed sine graph. The problem as hom HP is defined as follows. On the input, we have a sine graph G sigma, and we ask if there is a homomorphism of G sigma to HP. One of the most important results in this direction is settling the dichotomy of S-hom-HP by Brewster and Siggers. To state their result, I will first need to define S-core. A sign graph G sigma is a sign core, or shortly S-core, if every homomorphism from that graph to itself is a bijection. With this, I can state the result. The problem S-hom-HP is polynomial if HP has an S-core with at most 2 edges, and the problem is NP-complete otherwise. We are interested in a list variant of the problem. In the list variant of the problem, we have on the input not only a sign graph G sigma, but also for every vertex of G, we have a subset of vertices of H, the so-called lists. We ask if there exists a homomorphism between G sigma and HP, such that the images of vertices of G obey the respective lists. It is clear that every NP-complete case of S-hom-HP remains NP-complete for our list variant, so we can focus ourselves on sign graphs whose S-cores have at most 2 edges. However, there are many complex sign graphs with such property. The dichotomy conjecture for CSP was recently proved by Bulatov and Zhuk. Our problem can be formulated as a CSP, and therefore we know that there is a dichotomy in terms of complexity. However, here we are interested in a graph theoretical classification instead of an algebraic one. Let me briefly sketch the outline of the talk. We have a full dichotomy for the following cases of target graphs HP. First, if there are no bicolored edges in HP, then if the graph H is an irreflexive tree, and finally, if the graph H is a reflexive tree. Let me first focus on the case of no bicolored edges in HP. For this, I will need the definition of bi-R graphs. Let C be a circle with 2 specified points P and Q on C, which we call poles. A bi-arc is an ordered pair of arcs and S on C, such that N contains P but not Q, and S contains Q but not P. N is for north, S is for south. A graph H is a bi-arc graph if there exists a family of bi-arcs, one for each vertex of H, such that for every X and Y in H, not necessarily distinct, the following holds. If X and Y are adjacent, then neither NX intersects SY, nor NY intersects SX. If X and Y are not adjacent, then NX intersects SY, and NY intersects SX. We see an example of a bi-arc graph in the figure below. On the right, there is a reflexive path on 3 vertices, and on the left, we have its bi-arc representation. With the definition of bi-arc graphs, we can now state the dichotomy for this case. Suppose HP is a connected sign graph without any bicolored edges. If the underlying graph H is a bi-arc graph and HP is balanced or anti-balanced, then the problem list S-hom-HP is polynomial time solvable. Otherwise, the problem is NP-complete. This was proved by carefully combining the existing results for non-sign graphs. Let me now proceed to irreflexive trees. We will first consider some forbidden induced subgraphs. The graph F1 from the figure on the slide is forbidden as an induced subgraph in the underlying graph. This means that if H is not U2 caterpillar, the corresponding list homomorphism problem is NP-complete. This figure further depicts families of graphs which are also forbidden. Most of these have been ruled out based on finding a structure called chain in them. As that is quite technical, I refer to the paper for details. Now I shall describe polynomial cases. As we saw before, the graphs have to be two caterpillars. We also have the following constraints, which you can quickly check for the example below. The bicolored part of the graph forms a connected subgraph. Furthermore, there exists a dividing vertex on the spine such that the spine to the left is bicolored and the part to the right is blue. Also, the subtrees rooted at first d-1 vertices of the spine are bicolored, except for possibly the edges incident to leaves. Finally, from Vd plus 1 to Vk, all subtrees are blue. We call such two caterpillars good two caterpillars. We then have a lemma saying that whenever we avoid all the forbidden induced subgraphs we've seen before, the result is good two caterpillar. We then conclude with the dichotomy that the list homomorphism problem in this case is polynomial if HP is a good two caterpillar and is NP complete otherwise. Let me now more briefly sketch the situation with reflexive trees, which is in some sense very similar to the previous case. We have the result that the following reflexive tree is forbidden, no matter what the colors of edges are. This means that polynomial cases will be in this case caterpillars. We have also this family of forbidden induced subgraphs, this time more populated. The means for proving their NP completeness is either chains, large sign core, or other ad hoc arguments. Note that in the figure, dashed loops can be positive, negative, or bicolored. Finally, we define good caterpillars. We say that HP is a good caterpillar with respect to the spine V1 to Vk if H is a caterpillar, if the bicolored edges of HP form a connected subgraph, the unicolored non-loop edges all have the same color C, and there exists an integer d within 1 to k such that all edges on the path V1 to Vd are bicolored, and all edges on the path Vd to Vk are unicolored with color C. All loops at the vertices V1 to Vd minus 1 and all non-loop edges of the subtrees rooted at these vertices are bicolored. All loops at the vertices Vd plus 1 to Vk and all edges and loops of the subtrees rooted at these vertices are unicolored with color C. If Vd has a bicolored loop, then all children of Vd with bicolored loops are adjacent to Vd by bicolored edges. If Vd has a unicolored loop of color C, then all children of Vd have unicolored loops of color C and are adjacent to Vd by unicolored edges. And finally, if D is strictly lesser than K, then the loops of all children of Vd adjacent to Vd by unicolored edges also have color C. The definition does not look very appealing, but that is because the last 3 points of this list are covering the case for which there is an example on the right in the picture below. In that case, the dividing vertex has both a negative loop and a positive loop. That gives the dividing vertex more freedom in terms of what subtrees can be attached to it. And that is precisely what the definition captures. Again, we have a lemma saying that if none of the forbidden induced subgraphs is present, HP is a good caterpillar. The dichotomy then asserts that if HP is a good caterpillar, the problem of finding a list homomorphism is polynomial, and otherwise the problem is NP complete. Let me conclude the talk. In the paper, we proved a full complexity dichotomy and described polynomial instances for the following cases of targets HP. First, if there are no bicolored edges in HP, Then, if the graph H is a reflexive tree, and finally, if the graph H is a reflexive tree. In these days, we are finishing a dichotomy for trees in general. You can check our full paper, including the proofs on arXiv, and you can write me an email. Thank you for watching.